Okay, hello, my name is Josh Wheelan. In this video, I'll be explaining adiabatic reversible expansion and driving the equation starting from the first law of thermodynamics and writing it in terms of a first pressure, initial pressure, and initial temperature of a gas, or a fluid in this case. And we are going to be using it in terms of a ideal gas. So we're going to start off. So let's imagine you have about a pocket of air, basically kind of like a balloon. The pocket of air. It's at some position 1, you would say. So it has some pressure 1, and has some temperature 1 at this position. And let's say over time it rises up to a higher position 2. Okay, and at this position 2 it has a different pressure, and it has a different temperature because as it rises, technically think about you're on top of a mountain. You know how, notice how higher mountains have snow on top. The temperature is cooler up there, and then it is down here at the lower temperature. Okay, so let's look at this equation. So we're gonna be doing this in terms of the first law of thermodynamics. So our first law of thermodynamics states that some small amount of internal energy is equal to some small amount of heat minus a pressure times a small amount of volume. Now the key words here in this adiabatic reversible expansion, there's 2 key terms, adiabatic and reversible. What these words mean, first of all, adiabatic means that there is no heat added or taken away from the system. So this is the small amount of heat in the system of this equation. So we can basically cancel it out and say it's equal to 0. It's negligible. So this is 0. And reversible means that the pressure external, so the pressure outside of this pocket of air, is equal to, so let's say this is the internal pressure inside here, is equal to the pressure at this position 1 external. So we just don't have to write down different variables saying, well, we're at some position and it's the external and internal pressures. We can say they're one pressure. So we can go over here and say that P represents the pressure inside and outside. They're the same. So let's rewrite this equation in terms of an ideal gas. So we have du for an ideal gas can be written as CV, which is our heat of vaporization, times some small change in temperature, which means that our changes in internal energy are going to be dependent on small changes in temperature, because there is no heat change here. There's no heat added or taken away, so temperature controls this. Is equal to a negative. Now, in this case, we said this is in terms of an ideal gas, so we can basically substitute in what pressure is in terms of ideal gas. So we can rewrite pressure is equal to, now in this case, like the last equation over here, which we did last problem, we said that N is equal to 1, our number of moles of gas. So we can say that N is equal to 1 again, and we don't have to write it down. It's basically multiplying by 1, you don't need to have it there. So we can say that P is equal to our gas constant times our temperature over our volume. And we can rewrite that in for P. So we can say that, okay, negative R times temperature divided by our volume, or negative gas constant, multiplied by our small amount of volume. Okay, so now that we're here, we can start rewriting and moving things around so we have terms on the same side, like terms on the same side. So we can divide by temperature over here, and we should be good. So let's rewrite this equation and say that our heat of vaporization times, we can actually go ahead and start integrating. So times our small amount of volume, or temperature here, divided by temperature, is equal to our negative gas constant. Since these are both constants, we don't need to integrate them. We can just bring them on the outside of the integral. Times, since we got rid of temperature here, we can bring and multiply the dV on top. So dV, or small amount of volume, over top of our volume. Now, for our limits of integration, we want to write these in terms of our positions. So for our position 1 is always going to be on the bottom, and position 2 is going to be on top. So our starting temperature, like I said before, we have some temperature. So our first limit is going to be at position 1, the temperature at position 1. And it's to be raised to position 2, where the temperature is at a higher temperature. So temperature 2. Same thing for our volume. At position 1, it's at a certain volume, so volume 1, our pocket of air. And at position 2, the volume is expanded, so there's more volume, so it's at, let me write this in red so it's easier to see. It's at volume 1 and volume 2. Okay, so we can go ahead and integrate these and simplify it down to our, let's go over here. So CV, our heat of vaporization, times the natural log of, now we can take this and bring in our T2 and T1. The natural log of T2 over T1, our temperatures, I keep saying T2 and T1, okay, is equal to, same thing here, negative R, our gas constant, times the ln of V2 over V1. Okay, so now that we're here, so now we want to get our heat of vaporization and divide it by and bring it over here to our R, our gas constant. And then we are going to multiply and get rid of these ln's, or natural logs, by multiplying it, taking it to the exponential power. So these ln's are natural log and our exponentials are going to cancel out, so I'll show you here. So we're going to go down here, bring that here, and say that, okay, we're going to divide by our heat of vaporization, by our R, and we're going to take the exponential. So the exponential of the ln, or natural log, of T2 over T1 is equal to, okay, an exponential. So now we have our negative gas constant divided by our heat of vaporization, or ln, or natural log, of volume 2 over volume 1. Now, taking the exponential of a natural log cancels them out, and actually our constants here are going to be our exponential, bring up to an exponent now, sorry. So I can rewrite this as, these cancel out, these cancel out. So now we are left with volume 2 over volume 1 raised to the negative gas constant divided by our heat of vaporization. Okay, so since we're still working with a value of gas, we want to have these, since we have our, in terms of pressure, and we have volume here, so we need to substitute in our volumes. So we're going to take our volumes here and rewrite it again in terms of pressure. So we know our volume 2 is equal to, since we have we already have an R here taken care of, so we can just write this in terms of, okay, it's, oh wait, now, I'm trying to think. I'll explain this here. So we have our volume is equal to our gas constant times temperature 2 divided by our pressure 2. And our V1 is equal to our R, gas constant, times temperature 1 over pressure 1. So we can go ahead and multiply, divide these out technically, because since these are over top of each other, you can take and do like terms here. So we do our temperature 2 and our gas constant multiplied by our pressure 1 over top of, okay, our R value, again, our gas constant, times temperature 1 times our pressure 2. Or 2, shoot. Okay. And since these are not in terms of position, these are not dependent on positions, they're constants, our R's cancel out. So we are left with temperature 1 multiplied by pressure 1 over top of temperature 1 multiplied by pressure 2. And this is all equal to this right here, our volume 2 over volume 1, and it's raised to the negative R over CV power. Okay, so now we can basically substitute this in, and we want to get our temperatures on the same side. Technically, we could say this is to the 1 power. It's not there, but we could say it's technically that. So let's go ahead and get our temperatures on the same side. So we can rewrite this equation. We're going to multiply our temperatures together, which makes this a positive, or exponential positive now. So we're going to say our T2 over T1 to the first power multiplied by our T2 over T1 to the now positive, when you're bringing it over, R constant over our heat of vaporization. You can say these are the same thing as adding them together, adding exponents. So now we rewrite this in terms of having these together. So our temperature 2 over temperature 1 is equal to 1 plus our gas constant over our heat of vaporization. Okay, and then that leaves our pressures by themselves. So our pressure 1 over pressure 2 multiplied by negative gas constant R over our heat of vaporization. Okay, so now we're almost done with this. So we want to get our temperature, the exponent on this side, we want to cancel it out. So we leave only the exponents on the right side. So to do this, we want to actually multiply by the reciprocal of this, and that will give us, let's see, multiply by reciprocal and cancel these out. So T2 over T1, multiply by reciprocal of this, so it's R over, so let's see. This is the same thing as saying the CV power, so CV over 1, basically. So we could go ahead and rewrite this as, okay, we have CV plus R over CV multiplied by CV over our heat of vaporization over top of heat of vaporization times our gas constant. So that's a reciprocal. We need this both sides, so these cancel out. So now we are left with, okay, we have a temperature 2, our left side is now temperature 2 over temperature 1 is equal to, now we need to multiply with the reciprocal on this side, we'll just cancel out the exponents, our pressure 1 over pressure 2, now we need to raise them to the same, multiply by the same exponent. So we had a negative gas constant over heat of vaporization multiplied by, what was this R exponent here? So our reciprocal was heat of vaporization over heat of vaporization plus R. Okay, so this goes to what? We have a negative R times CV over CV squared plus R. Since these are same terms, we can actually cancel them out, and we are left with an overall exponent, our final answer here, negative gas constant over our heat of vaporization plus a positive gas constant. And this is actually our answer. All right, thanks for watching.